Hello. So this is the second part of the explanation of the topic of uniform continuity. The first part is in a separate video which is linked down below. So in this part we are going to discuss what kind of functions are not uniformly continuous. We will state the sequential characterization of the statement that a function is not uniformly continuous on a set, and we will prove rigorously that the function f of x equals to x squared is not uniformly continuous on the interval 1 to plus infinity. Let us recall the definition of uniform continuity. So let's just recall that a function f from an interval ab to r is uniformly continuous on a set I that's not empty if for every epsilon greater than 0 there exists a delta such that whenever we take 2 points inside of the interval I such that the distance between those 2 points is less than delta, we know that the distance between the values of the function at these 2 points is less than epsilon. And let's just recall from the previous video, which is linked down below, what is the intuitive understanding of uniform continuity. So this function whose graph is depicted here in the red color is uniformly continuous on this interval I. It's actually the function f of x equals to x squared that is plotted in here, and we did prove in the previous video that this function is indeed uniformly continuous on the interval 0, 1. So if you assume that this point over here is 1, then we actually proved that. So here is one way to understand uniform continuity intuitively, and it's very helpful because sometimes if we do not know beforehand whether a function is or is not uniformly continuous on an interval, this is something, this way of thinking about uniformly continuous function, it can help us to have a clue and to somehow intuitively try to understand whether or not this function might be uniformly continuous or maybe not. So let us fix an epsilon. Suppose that delta is some positive number. And so let us look at this cylinder where epsilon is the diameter of the cylinder and delta is the height of the cylinder. So I call it a height. You can also call it a width, whatever you prefer. I'm just going to refer to it as a height. Okay, so this is the height of the cylinder, and it's the height is delta. So let's just recall that the function f of x is uniformly continuous on this interval I if and only if, whenever we fix a positive number epsilon, we can pick a delta in such a way that if we take this cylinder and if we kind of thread this function inside of the cylinder, and if we imagine that this graph of the function is made of a wire, and we sort of put the cylinder through this wire in such a way that the wire is inside of the cylinder, but remember, we are not moving the wire in any way. We are not rotating it, we are not moving it in any way. And we are making sure that the side of the cylinder is horizontal. The side of the cylinder right here, okay, is horizontal. So we can pick a delta, we can pick the height of the cylinder or the width of the cylinder in whatever way you want to describe it. We can pick it in such a way that we can take this cylinder and drag it through the curve in such a way that the sides of the cylinder remain horizontal all the time, and the diameter of the cylinder and the height of the cylinder do not change. So as we drag this cylinder throughout the curve, of course, the cylinder remains the same cylinder, so its diameter and its height do not change. And it is very important to understand here that when we say that we drag the cylinder, we always make sure that the sides of the cylinder are horizontal. Because of course, if we could rotate the cylinder, then this intuitive understanding doesn't make sense. Because I could just, if I was allowed to do something like this, if I was allowed to do something like this, so this would be a cylinder whose sides are not horizontal, right? This is the side of the cylinder and it's not horizontal. And if I could rotate the cylinder, then this intuitive understanding, it doesn't make sense, because I can thread this kind of cylinder through any kind of wire as long as it's continuous. So then that of course there is a difference between a continuous and a uniformly continuous function. So remember, this intuitive understanding, it's good when you remember that the sides of the cylinder always have to stay horizontal. All right, I feel like I already said more than I have to in this situation. So in this video, we are going to discuss, well, what kind of function is not uniformly continuous. So here is our question. What kind of functions are not uniformly continuous? So let's just give a definition of a function that's not uniformly continuous. So all we have to do is we have to take this definition 1 over here, and this is the definition actually, and we are just going to negate it. Okay, so negate definition 1. So a function f from interval ab to the set of real numbers is not uniformly continuous on a set I that is a subset of AB, non-empty set, if, so now we are going to go ahead and negate it. And if you remember, when we negate a statement that is written using quanters, instead of for every, we write exists, and instead of exist, we write for every, and we kind of try to connect this in such a way that the statement makes sense. So the negation of this statement over here is going to be there exists epsilon greater than 0 such that for every positive delta there exist a couple of points x1 and x2 in the interval I, such that even though x1 minus x2 is less than delta, so these 2 points can be actually really close to each other, the distance between the values of the function at these 2 points is bounded from below by this number epsilon. So this number epsilon, it exists. It's a lower bound for the distance between the value of the function at 2 points that can actually be as close to each other as we want. So let us try to develop an intuitive understanding of this definition that we have just written of what it means for a function f to not be uniformly continuous on some interval. So let us consider this example here. So we have here a function y equals to x squared, but instead of looking at the interval 0, 1 like we did on the previous video, now we are going to look at the same function but on a different interval from 1 to plus infinity. And so we are going to try to understand first intuitively whether or not this function is uniformly continuous on the interval 1 to plus infinity. And actually I made a mistake in here. I didn't mean to include plus infinity in the interval. Okay, so let us try to look at the graph of the function y equals to x squared, and let's just try to understand if this function here is or is not uniformly continuous on the interval from 1 to plus infinity. So I'm not going to do the cylinder thing just yet. It's coming. So far, I just want to make this observation here. So let's look at these 2 points, x1 and y1. So these points are definitely on the interval from 1 to plus infinity, the way they are marked here. Agree? Let's just say that the distance between these 2 points is delta. So the delta is just the distance between 2 points. That's all that delta means so far. Let's just look, so the distance between the points f of x1 and f of y1 is right here. Do you see? So that's the distance between these 2 points. Now, let us take 2 points, x2 and y2, but now x2 is larger than x1, right? So we moved to the right. The distance between x2 and y2 is still delta. We made sure that we just chose x2 and y2 in such a way that the distance between them is still delta. However, x2 is larger than x1. Now, if we look at the distance between f of x2 and f of y2, if we compare this distance with that distance, well, so if I call this distance over here to be a1, and if I call this distance over here to be a2, which one is larger, a2 or a1? Well, if you have given it a little bit of thoughts, you will see that a2 is definitely larger than a1. So the observation here is that even though the distance between x2 and y2, and that distance actually is the absolute value of x2 minus y2, so even though the distance between x2 and y2 is the same compared to the distance x1 and the y1, which is the absolute value of x1 minus y1, the distance between f of x2 and f of y2 is larger than the distance between f of x1 and f of y1, which can be expressed in terms of this inequality over here. So it seems like even though we have the distance between the x coordinates fixed to be delta, the further away we move to the right, so the further away we move to the right, the larger the distance between the values of the function becomes. So let us now translate this observation into the terms of the cylinder. So remember how we discussed an intuitive understanding of uniform continuity using a cylinder in the previous video? So that video is linked down below, just in case you want to recall what that was. So let's just now imagine that this graph of the function y equals to x squared, that it is made out of a wire. And that wire is fixed. We are not going to move that wire around. We are not going to rotate it or move it. We will not do anything. It's just made out of a wire. And now let us consider this cylinder. So the diameter of the cylinder is this number a2, and actually let's just make this diameter of the cylinder just a little bit slightly larger than a2. I just want to make sure that the curve fits into the cylinder. You will see in a moment what that means. So it's just slightly larger than a2. You can say that it's a2 plus some very tiny number alpha. So in any way, so epsilon is fixed. Epsilon is larger than a2. And remember what a2 was? a2 is this distance between f of y2 and f of x2, right? So the diameter of this cylinder is just slightly bigger than this distance, okay? And the width of the cylinder, or the height of the cylinder, whichever way you prefer to call it, is delta. And this delta is the distance between x1 and y1. and it's the same as the distance between x2 and y2. So delta is also fixed. Okay, and so we have this cylinder, okay, and I drew this cylinder over here. And so you can check the width of the cylinder is delta, and the height is just a little bit slightly larger than A2. And again, this is the same cylinder, but it's positioned on a different point of the graph. And the width of the cylinder is still delta, and the height of the cylinder is still epsilon, which is a little bit larger than A2. But since A2 is larger than A1, the diameter of the cylinder is also larger than A1. So you can imagine that if we have this cylinder, there is no problem for us to drag this cylinder down here to the left along the curve in such a way that its side always stays horizontal. So there is no problem going to the left. And the reason for that is that the further away to the left we go, the smaller the distance between between the values of the function at 2 points that such that the distance between them is delta, the smaller that distance becomes, right? So if here I had distance between the 2 points to be delta, and the distance was A2, then if I move to the left, the distance between these 2 points is still delta, but the distance between the value of the two values of the function is smaller. Okay, so there is no problem with dragging this cylinder to the left, and actually we could drag this cylinder all the way to the left. So what does it mean? It means that if we were looking at this interval from 1 to this point y2, the function f is definitely uniformly continuous on this interval. But this is not the interval we are talking about. We are talking about interval 1 to plus infinity. So the question now is, can we drag this cylinder along the curve to the right? Can we drag this cylinder along the curve to the right in such a way that the sides of the cylinder always remain horizontal? If I was willing to turn the cylinder, there is no problem. I could just turn the cylinder and, then I can move it along the curve everywhere I want. But this is not the definition of uniform continuity. In order to confirm that the function is uniformly continuous on the interval 1 to plus infinity, I should be able to take this cylinder and drag it to the right. I can move it up, but I cannot turn it. I have to drag it to the right in such a way that the side of the cylinder always remained horizontal. And so if I can do that, if I can move the cylinder all the way to the right, and if I can go as far to the right as I want along the curve, and still have the curve as a wire inside of that cylinder, then I will know that my function is uniformly continuous on the interval 1 to plus infinity. So now I want to ask you guys, you are listening to this, what do you think is going to happen if I try to drag this cylinder to the right as far as I want? So I'm going to repeat the question. What do you think is going to happen if I take this cylinder and I drag it to the right in such a way that the side of the cylinder always remains horizontal? Am I going to be able to move to the right as far as I want? Or am I going to get stuck somewhere? So the answer to this, I'm curious what is your answer, and I would like you to write it in the comments down below what your answer was before I told you the answer. I'm just curious. So the answer to this is that at some point we are going to get stuck. So we are going to have a situation like this. So this is our cylinder of the diameter epsilon, and the width or the height, whichever way you want to call it, delta. And we are going to have a situation where the curve it's made out of wire, and it's really snug in this cylinder, right? So it's kind of, the cylinder is now stuck. Like if I can't move this cylinder to the right any further while keeping it horizontal. And I can't move the cylinder up because there is this portion of the curve is gonna keep me from moving it up, right? And I can't move the cylinder to the right because this portion of the curve prevents me to move it to the right. So this cylinder is stuck. So when I get stuck, the only way to move forward with the cylinder would be to turn it, right? However, as we mentioned, turning the cylinder is not something that is in the definition of uniform continuity. So from our observation, we can make a conjecture. So since we can't move this cylinder to the right as far as we want, our conjecture is that the function f of x equals to x squared is not uniformly continuous on 1 to plus infinity. And why did I say that this is a conjecture? Why didn't I make it a statement? Well, this is something that we see intuitively using this whole idea with the cylinders, but we didn't prove it rigorously. So whenever we have an intuitive idea that it seems right to us, but we do not have a rigorous proof of that, we can say that this is a conjecture. And the conjecture is true if we prove it rigorously, and then conjecture may turn out to be not true if we don't prove it. But the point is that when we look at a function, before we try to prove that the function is uniformly continuous or is not uniformly continuous, we need to have some kind of intuitive idea of what this function might be, right? So if the function is not uniformly continuous, it probably is not useful to try to prove the function is uniformly continuous, right? So in that sense, this is why we want to have a conjecture. Okay, so the next question that we are going to address is how do we prove that a function is not uniformly continuous, right? We did prove that the function f of x equals to x squared is uniformly continuous on the interval 0, 1, on the open interval 0, 1. We proved that in the previous video. So we kind of have an idea of how to prove that the function is uniformly continuous. Well, how do we prove that the function is not uniformly continuous? So possibility 1 is just use the definition, right? So we did write down here in this definition 2 what it means that the function is not uniformly continuous. So we just go ahead, look at this definition, and we prove that this is true. Whatever it is that is stated in this definition, we prove that it is true. And if we prove this, then we know that the function is not uniformly continuous on our set, whichever set it is that we are considering and whichever function it is that we are considering, right? So our first possibility to move forward is that we prove, we use definition 2. Now possibility 2 is that we use the following theorem. And I'm going to state the theorem. If you would really like me to make a video and to prove the theorem, I'll be happy to do so. Otherwise, I'm just going to state the theorem and show you how to use the theorem and to prove that the function is not uniformly continuous. So the theorem is the following. So let f from AB to R be a function. So of course we are talking about the situation where A is less than B, so we're not talking about an empty interval. And so let I be a subset of AB such that I is not empty. So suppose that there exist two sequences xn and yn in the interval I. So that means that xn and yn are in the interval I for all n natural numbers. And the sequences are such that if we look at the distance between xn and yn, so this would be the distance between xn and yn. We just take xn minus yn absolute value. It converges to 0 as n approaches infinity. And at the same time, there exists epsilon greater than 0 such that the distance between f of xn and f of yn is greater than or equal to epsilon, right? So even though the distance between the corresponding terms of these two sequences goes to 0, the distance between the values of the function at these two terms is bounded below by this number epsilon. And this is true for every n natural number. So if this hypothesis is true, then the function f is not uniformly continuous on the interval I. Okay, so I'm not going to prove this theorem right now. I can make a separate video with the proof of the theorem. However, let us discuss this theorem. So let's just discuss this theorem on the same example of the function y equals to x squared. So I'm gonna plot the graph of the function. I'm not being particularly precise with the scale in here. And so let's just say that this is 1 here. And so that would be 1, that would be the scale. And so let's just say that we have two sequences. So one of the sequences is xn. So let's just say that this is my x1, x2, x3. And the other sequence is yn. So this is going to be my y1, y2, y3. So you may notice that I made the picture in such a way that this distance between x1 and y1 and x2 and y2 and x3 and y3 is becoming smaller and smaller. So this is just to make sure that we are consistent with this hypothesis that is highlighted in yellow here, that the distance between xn and yn converges to 0 as n approaches infinity. Okay, so we have these two sequences here. So we have that xn minus yn approaches to 0 as n approaches to infinity. And yet we have a situation where f of y1 minus f of x1, f of y2 minus f of x2, and f of y3 minus f of x3, it's greater than or equal to some number epsilon that is greater than 0. And yet we have a situation where f of xn minus f of yn is greater than or equal to epsilon for all indices n, where epsilon does not depend on n, right? So if we can construct such two sequences with these properties that are outlined here, then that means that the function f is not uniformly continuous on the appropriate interval. So we have been talking here for the case y equals to x squared, and the interval I is the interval 1 to plus infinity. So now we can come back to our example and we can finally prove that the function f of x equals to x squared is not uniformly continuous on the interval from 1 to plus infinity. So our strategy is going to be to use the last theorem. So we are going to want to construct two sequences xn and yn such that all the terms of these sequences are in the interval 1 to plus infinity. Remember, the sequences have to be on that very same interval on which we are trying to prove that the function is not uniformly continuous. So in our case, it's the interval 1 to plus infinity. So we want to make sure that xn and yn are in this interval for all n. And these conditions that we have written over here, we want to make sure that these conditions hold. So I'm going to write them down again. We want to make sure that xn minus yn converges to 0 as n approaches to infinity, yet at the same time xn squared minus 1 squared is greater than or equal to some number epsilon, where epsilon is some positive number that does not depend on n. So this is going to be our strategy. So at this point, some students say, well, this seems to be such a complicated task. How on earth am I gonna come up with these two sequences? And then I say, well, actually, we have a pretty good understanding of what these two sequences should be. Look, over here, from our previous example, we see that where the function fails to fulfill the conditions of uniform continuity is when we move further and further away to the right. So it seems like our sequence xn should be something like this. x1, x2, and x3 is going to be even larger, x4 is going to be even larger, and that corresponds to the sequence over here, right? And so can you think of a sequence like that, that each consecutive term of the sequence is larger than the previous one, and the sequence actually diverges to plus infinity? So if you end up having an example other than what I'm going to tell you now, can you please share it in the comments? So I'm gonna take xn to be n. So for me, x1 is gonna be 1, x2 is gonna be 2, x3 is gonna be 3, and so on and so forth. So note, limit of xn is plus infinity. So this is not something that we had to do according to the theorem. So why did we choose such a sequence? And why did we do that is because when we did our observation of the graph, we realized that our cylinder gets stuck on the graph that's made out of a wire when we move to the right. So if I make the delta smaller, then I would still get stuck as I move to the right, but just a little bit further along. If I made the delta even smaller, I would still get stuck when I move to the right, just a little bit further down the right. So it's from this example here, from this observation, that we see that the function f fails to meet the requirements of uniform continuity when we move further toward the right. So it's all about this interval, that the right bound of the interval is plus infinity, is actually that there is no right bound for the interval. Okay, so that's why we choose this sequence that way. So because of our observations above. So the reason why I'm explaining all of this in so much detail is just I want you to have the confidence that if you come up with a different example, you can do all of this on your own, because sometimes my students have this kind of lack of confidence. They understand everything that I explain on the board. They understand the lecture perfectly, but then when they go and they need to do their own homework example, all of a sudden they feel like, well, I am not sure I can do this without my teacher. Well, you can. The thing is that you can come up with what this sequence is without me telling you what it should be, because of this observation, right? Because of this observation, and because you kind of see that the terms of the sequence, they should be chosen in such a way that every consecutive term is larger than the previous term, and that the sequence overall diverges to plus infinity. And so the easiest choice would be xn equals to n. So you could have thought of that yourself. I don't want you to think that it's something that you cannot do. I want to give you the tools of being able to think of sequence like that yourself. So now we see what we have accomplished. We have this one sequence, xn equals to n. Now we have to come up with a sequence yn. So now the question is, well, what do I make this sequence yn to be? So, well, we have to make sure that the distance between xn and yn goes to 0. So the easiest way to make sure that that happens is to let yn to be xn plus 1 over n. So I'm taking what I had for xn and I'm adding 1 over n. Why 1 over n? Because 1 over n converges to 0 as n approaches infinity. So my sequence yn is going to be n plus 1 over n for all natural numbers n. Okay, so then if I check these conditions, xn minus yn, so xn is n plus 1 over n, and yn is n. I'm just going to get 1 over n, and this is certainly something that converges to 0 as n approaches to infinity. So this condition over here, it holds. So this condition over here, I'm going to denote it by 3. So this condition 3 holds. However, we now have to verify that xn and yn are both in the interval from 1 to plus infinity. So let's see, is that true? So xn equals to n is always greater than or equal to 1 for all n natural numbers. So xn belongs to the interval 1 to plus infinity for all n natural numbers. And so similarly, yn, which is n plus 1 over n, this is actually strictly larger than 1. So yn is in the interval 1 to plus infinity for all n natural numbers. Okay, so now we have verified this condition that xn and yn should be both in the interval 1 to plus infinity. So now we need to check, is it true that this statement 4 holds with this epsilon that doesn't depend on n? Because if we can show that 4 holds, then by the theorem that we have just stated a few minutes ago, what's going to happen by this theorem? I'm going to give you just a few moments to think about that. If we can show that 4 holds by the theorem, what's going to happen? So note, if 4 holds, then by theorem, the function f of x equals to x squared is not uniformly continuous on the interval 1 to plus infinity. Let us now consider xn squared minus yn squared, right? So this is from condition 4. This is why we are considering it, because of the condition 4. We want to show that this distance between xn squared and yn squared, that it is bounded from below by some positive number that doesn't depend on n. So I'm just gonna plug in. So xn is n, so this is gonna be n squared minus, and yn is n plus 1 over n. And now I'm just going to go ahead and simplify. So this is going to be n squared minus n squared minus 2 times n times 1 over n and minus 1 over n squared. So this is going to be, so n squared and then the n squared cancels. This also cancels. So we're going to have 2 plus 1 over n squared, which is just 2 plus 1 over n squared, which is definitely greater than or equal to 2. So let us set epsilon equals to 2, then xn squared minus yn squared is greater than or equal to 2 for all natural numbers n. So we proved that condition 4 holds. So we proved that condition 4 holds. So we showed that 4 holds. So in summary, we showed that the hypothesis of the last theorem holds for the function f of x equals to x squared and the set 1 to plus infinity. So hence, by the theorem, the function f of x equals to x squared is not uniformly continuous on the interval 1 to plus infinity. And this was a rigorous proof, so now we can write QED. This is no longer a conjecture, this is a rigorous proof. So now we know for sure that our function f of x equals to x squared, that is plotted over here, this function is not uniformly continuous on the interval from 1 to plus infinity. For your homework, after having watched these 2 videos, I would like to recommend for you to prove that the function 1 over x is uniformly continuous on the interval from 1 to plus infinity and is not uniformly continuous on the interval 0, 1. Okay, so with this function, you should be able to carry out the proofs in a way that is very similar to how we proved similar statements to the function x squared. So if you like this video, if it was helpful to you, please give it thumbs up. Because if you give it thumbs up, then YouTube is going to promote this video more and other people will be more likely to find this video. If you like this channel and this video, please subscribe to it so you will know when new videos are coming up. And also your subscribing to these videos, to this channel, is going to support my work because I'm a freelancer. So the more subscriptions I have, the better it's going to be in terms of supporting my freelancing work. And of course, it also matters in the way that YouTube promotes these videos. So I hope that you like this video. So if there are any questions, if there is something that you didn't understand in these videos, please feel free to write this in the comments. I would like to hear your feedback. I'm curious how this homework assignment is going to go for you, if what you have heard in these two videos, if what was explained there is going to help you to prove these two statements that I have assigned for you. So I'm curious what you think about that, and if there are any other mathematical topics that you would like me to cover in future videos, please also write this in the comments or just send me an email. I'll be happy to hear from you. And so I hope to be in touch with you through these videos sometimes again in the future.